right, welcome back to AP Chem. This lesson in Unit 2 is on intramolecular forces and potential energy. So intramolecular forces are just the forces between two atoms that are in the same molecule. The word that we most often use for this force is a bond. So intramolecular forces are just bonds. So when you see that, don't freak out. It literally just means a bond. So ionic, covalent, or metallic. When we're dealing with these forces, we want to look at the strength of the interaction, and that can also deal with the energy of the bond. So we use Coulomb's law to kind of understand the strength of the forces between cations and anions in an ionic bond. So remember that Coulomb's law is force equals charge over distance, basically. So the larger the charge, the stronger the interaction will be, the stronger that force will be. So force increases with increasing charge. The smaller the ion, the stronger the interaction will be as well, because if you have a smaller ion, that distance between the charges decreases. And so since force is charge over distance, force and distance are inversely related. So the smaller the distance, the greater the force will be. The energy in an ionic compound is called the lattice energy. This is how much energy change takes place when those ions are packed together to form an ionic solid. So when the bond forms, the lattice energy is how much energy is released when that bond takes place. We can look at the different lattice energies for different ionic compounds and compare them to see how strongly ions are attracted to each other within different types types of compounds. So again, lattice energy is how much energy is released. Whenever we form a bond, we're going to be releasing energy. And so in chemistry, when we're releasing energy, the number will have a negative sign because we're looking at what's being given off, what's being lost by the system. And the system in this case is our ionic compound. So just be aware that when you do a calculation for a lattice energy or a bond energy for any type of compound, that answer will always be negative because energy must be released to form those bonds. In this example, we want to find the lattice energy of lithium fluoride. So typically in this type of problem, we just want to find 1 mole, the energy for 1 mole. And so you might see like a half in front of one of your reactants because we need to get that down to 1 fluorine. So we'll kind of go through what we do with that on the calculation side. So the first thing that needs to happen in order for us to calculate this lattice energy is that lithium needs to become a gas. So that we call that sublimation. So lithium goes from the solid state to the gaseous state. And we're given in the problem that takes 161 kilojoules per mole. The next thing that happens is lithium needs to be ionized. So this is often called the ionization energy. So we have our lithium gas, and it's going to become a positive ion because that's what lithium does. And it's going to lose that electron. And we're given that takes 520 kilojoules per mole. Next, we have to break the bond in F2. So we have our 1/2 F2. We only want one of them, and we want it to be single, so we're going to wind up with that. So the bond energy of F2 is 154 kilojoules. But we have this half. We want to get rid of that, so we're going to divide it by 2, which is going to give us 77 kilojoules per mole of fluorine, single fluorine produced. Next, we need to turn that fluorine into an ion. So fluorine gains an electron to become an ion. So this is its electron affinity. It's going to become negative, and that is negative 328 kilojoules per mole. So that energy is being released. And then lastly, we want to put it together. So we have our lithium ion in the gaseous state, combining with our fluorine ion in the gaseous state to make lithium fluoride in the solid state. That's our lattice energy, which is 1047 kilojoules per mole. And then to figure out the energy of this whole process, we just add these up. Make sure you pay attention to the positives and negatives. And we wind up with negative 617 kilojoules per mole, which makes sense. It needs to be negative because we're creating a bond, so that releases energy whenever a bond is created. Ionic bonds are really strong because we're dealing with that force of attraction between oppositely charged particles. So it takes a lot of energy in order to break those bonds. And so if we want to melt or vaporize an ionic solid, it's going to require a lot of energy. We see this as endothermic. Endothermic means energy is required. We have to add energy to that system in order to break those bonds. So just like it releases energy when the bonds are formed, in order to break the bonds, we have to put energy back into it. So the ionic compounds are in these crystal structures, crystal lattices, and in that crystal structure, they're very organized in regular patterns, and each ion is surrounded by ions with an opposite charge. And so you have a positive ion that's completely surrounded by negative ions, a negative ion that's completely surrounded by positive ions. They're really stable in that state, and they don't want to break apart from that. So that is why the ionic bonds take so much energy to break, because those ions are really stable being surrounded by opposite charges. So as we said with ionic compounds, Coulomb's law is used to calculate how much energy is between the two charged particles. But Coulomb's law can also be used for covalent compounds as well, because force is just charge over distance. And when we're dealing with covalent compounds, even though the atoms themselves are not charged, we're still dealing with the attraction between charged particles. In a covalent compound, those charges are the nucleus with the positive protons and those shared electrons, which are negative. So we're still dealing with positive and negative charges, even if the atoms are exactly the same. So if we have two identical atoms, we have a couple different interactions happening between charges, right? So within our system here of our two atoms, we have two energies that are repelling. We have the protons in one atom repelling the protons in the other atom because they're both positive. So positive and positive repel. We also have the electrons all repelling each other because they're all negative. So they're going to repel as well. But we do have one energy that is favorable, that wants to form a bond, and that is the proton and electron attraction, that attraction between positive and negative charges. So everything in science, everything in chemistry wants to have the lowest possible energy. So the atoms are going to move together in a way that minimizes the amount of energy between them. So basically, we want that sum of the attractive and repulsive energies to be minimized. And once it reaches that minimum amount of energy, that is where the bond forms. And the distance that occurs at, how far away those atoms are from each other, is how we find the bond length. So here's a chart. This is also in your book. But we have two hydrogen atoms, two identical atoms. So if they're far enough apart, they're not going to have any interaction at all. No attraction, no repulsion. So on this graph, that's like way up here. As they move closer together, they're going to start to interact more. So the closer they get, the more interactions they have, and that energy is going to decrease because now we're having those repulsive interactions, but we're also having those attractive interactions. So basically what's going to happen is these atoms are going to get to a point where they're close enough to achieve this minimum amount of energy, which you can see here on this graph. This is our minimum amount of energy. This is the sweet spot. This is where these atoms will form a bond. And that distance between them is the bond length. That is the optimum distance to get the least amount of energy out of this system. If they start to get any closer together, they're going to start repelling each other again. And so they're going to move apart. The energy is going to go back up until it kind of stabilizes out here. But this is where the bond will form when we reach that minimum amount of energy. So like we said, bonds are just forces that hold those atoms together and cause them to behave in a particular way. They have their own unique set of properties now that they're bonded together. And the reason that bonds happen is due to the octet rule, so that the atoms can get a full octet of 8 valence electrons. But the reason that they do that is to reach this lowest possible energy. So the bond will only occur if the group of atoms together, like bonded together, has a lower energy than separate atoms and the atoms that are not together. So the length of the bond and the strength of the bond, how much energy it has, are influenced by two main things. First, the size of the atoms, and second is the bond order, which just means whether the bond is single, double, or triple. If a bond has a higher energy or a higher order, it'll have a larger bond energy, and it will also be shorter. So like a triple bond has more energy than a single bond, and it's also a shorter bond. The energy required to break a bond depends on the situation. It depends on which elements are bonded together, and it also depends on what type of bond it is, single, double, or triple. So basically what scientists have done over the years is calculated the average bond energy in these different bond types. So between two of the same atom with a single, double, or triple bond between them. There may be slight variations in real life because, depending on what that atom is bonded to on the other side, like it might not only be bonded to one thing. So that could cause slight differences. But basically, we just use these average bond energies to kind of give us an approximate value. And so we have a list in our book on page 374 that gives us the average bond energies for a bunch of different bond types between different elements and different orders, single, double, or triple, so that you can kind of use those to approximate the energy of a compound based on the types of bonds that are involved in it. So we can use the energy of a bond to figure out how much energy is in a reaction overall, based on the types of bonds that are being broken and the types of bonds that are being formed. So if you look at this reaction, we've got hydrogen gas reacting with fluorine gas to form hydrofluoric acid. So when we look through this reaction, we see that we have one hydrogen-hydrogen bond that needs to be broken and one fluorine-fluorine bond that needs to be broken. And then we're going to form two HF bonds because there's two hydrofluoric acids over here. So we can calculate this by taking the energy required to break these old bonds on the reactant side, and and then finding the energy released when we form these new bonds. So basically, we're going to take these bond energies, add them together, and then subtract these bond energies. This gives us what we call delta H. Delta H here is the bond energy, or you might also see it called the bond enthalpy, but they basically mean the same thing. We're just looking at how much energy is in this reaction. And remember that the energy required to break a bond is always going to be positive because we have to put work into it. But then when we form a new bond, that energy is going to be negative because we're releasing energy. Energy is being given off. In this question, we're asked to find the delta H for this reaction where methane, CH4, is reacting with chlorine and fluorine. So our delta H is always going to be the reactant bond energy minus the product bond energy. So our book gives us a table of different bond energies, and basically what we're going to do is add them up. So on the reactant side, we start with CH4. We have 4 carbon-hydrogen bonds, plus we have 2 chlorine-chlorine bonds and 2 fluorine-fluorine bonds. And those are all single bonds. And then we're going to subtract our product bonds. So on this side we have 2 carbon-fluorine bonds and we have 2 carbon-chlorine bonds. We also have 2 HF bonds and 2 HCl bonds. So then we can look in our book to find the values. So on page 374 we have this list. So we just look up each of these bond types. So for CH, it is 413. For chlorine-chlorine, it is 239. So these are the individual bond energies of each of the bonds that's either being broken or formed in our reaction here. So then what we can do is go ahead and add up these totals on each side. So our reactant total here is 2,438. And our product side works out to 3,632. So then we just go ahead and subtract those. And we wind up with negative 1,194 kilojoules per mole.